afternoon, everyone. Thank you for joining us today for our Calculating Energy Cost webinar. My name is Lorena, and I will be co-hosting today's webinar. I will be monitoring chat throughout the session for any questions, and also will be conducting a polling survey at the end of the webinar. Today, we're going to be covering some examples of how you can calculate energy costs so that you can take that back to your facility and be able to calculate your own costs and hopefully be able to save energy and money. Before we get started, we also want to thank our co-sponsors, Energy Trust of Oregon and Northwest Energy Efficiency Alliance, which you'll see their logos on the bottom of the screen. We work real close to them, and our customers appreciate that because it helps keep us aligned to help eliminate any confusion regarding energy efficiency and renewables. Before I introduce the instructor, I would like to show you some tools that you'll be using during the webinar. To the right of your screen, you'll see the participants window, where you'll see all the lists of attendees that are joining us today. Right underneath all the names, at the bottom of the participants window, you'll also see a button that has a little hand and it says raise hand. At any point, if you have something you want to share or you have questions that you want to ask over the phone, feel free to click that and then we'll unmute you and have the instructor ask you. There also is an activity where the instructor will have you practice using that. Right underneath the participants window, you'll see a chat window, and that's where you'll be able to send me any questions or thoughts or suggestions, and I'll insert them during the session. But we'll also have some dedicated time at the end of the seminar or the webinar to answer those. And at the end of the session, right underneath that, you'll also see a polling that will come up that you'll be able to take a few minutes to give us your feedback. On the top left corner of your screen, right underneath the Quick Start tab, you'll also see some tools that we call the annotating tools. There's an arrow, there's a T, a line, a square, a marker, and an eraser, and you'll be able to interact with us using those tools throughout the session. The instructor will let you know when to use those. So go ahead and get started. Again, if you have any questions or any issues that come up, go ahead and send them through chat to me. John McLean is going to be your instructor today. John has a wide range of experience in the utility industry, over 42 years, which includes field operations, information systems, corporate planning, budget manager, and energy efficiency programs. He also holds a bachelor's degree in business administration and an MBA in organizational effectiveness. John is currently the project manager for our training education group, and out of all the instructors that we work with, John is a lifelong learner and is also a current adjunct faculty at Clackamas Community College and now also Marihurst University. So he knows a lot, so ask him lots of questions and challenge him, or feel free to share as well if you have some thoughts or examples that he can use during the session. And we want it to be interactive, so feel free to submit questions and engage with John in some of the activities. So John, we'll go ahead and get you started here.
Thank you, Lorena. Today's agenda, as you can see, is going to be how is electricity measured, how do we calculate savings for projects, how do we do a simple evaluation, and who do I call to get advice if I want some help. For this seminar, we assume that the attendees are non-technical management staff and other interested professionals who depend upon energy-intensive systems in their place of work, campus, retail, government, or industrial process. We also assume you desire to learn, to review the fundamentals. Many of these fundamentals apply to other resources such as natural gas, water, carbon footprint. So even though we're going to use electricity as our examples, the concepts can apply to other resource management issues as well. In 1 hour, we can't cover all the needed topics, but we can focus in on the ones that I most commonly hear questions from our customers. And all of that begins with the ability to calculate energy costs for equipment, whether you're at home, office, or industrial process. So with that, here's the first sheet on the basic characteristics of electricity. And the most common analogy for understanding electricity is the garden hose, the water system at your home. And when you hear the term around work, the volt we have volts issues or volts in any way, amount of force or potential applied. Think of your garden hose out front, and that is the equivalent to the water pressure. Sometimes when all the sprinklers in the neighborhood are on and you want to take a shower, you will find that your water pressure may not be high enough for that piece of equipment to give you the kind of shower you want. The same kinds of things can happen around the workplace, especially offices and manufacturing where there's a lot of energy-using equipment around. So if you hear about volts, think about pressure. The second term that may come up is the amp, the amount of electrons flowing. Electricity is all about electrons moving through and around a wire. The bigger the size of that wire, the more electrons. This is equivalent to the garden hose again. If you need to move a lot of water from point A to point B and you have like a rainbird sprinkler or something that requires a lot of water to work effectively, you may have to go from a half-inch hose to a larger 1-inch hose. When the fire truck pulls up, hopefully in your neighbor's, not your house, they've got a 3 or 4-inch hose that they're putting a lot of water through. So think about those two concepts. The volt is the pressure, and the amp is the volume. And if you multiply one times the other, that's where you will come up with the mighty watt. So when we talk about power and energy, we are usually talking about watts, which is volts times amps. Now, this is the formula for single-phase power. This is the most common. Almost all residential has single-phase, and most of the commercial has single-phase. There are a few terms that we won't discuss today, but I want to make sure you have them. If you have three-phase power, then you would have volts times amps times the square root of 3 times something called the power factor. This applies to some of the largest commercial and industrial customers. Mostly when they have large motors, there can be a power factor on the electric bill, and those might be some terms you hear about. The last one is you may hear about ohms. That's the amount of resistance to the flow. Copper wire would have less resistance than aluminum wire. And so sometimes you may hear the word ohm, but I don't think you'll ever see it on your electric bill. So those are common terms that we'll be using today on the top half and not the ones in the gray area. So when we look at our bill, about 90% of the energy bill depends upon understanding the term kilowatt hour, kWh. And whenever we deal with acronyms, it's important to understand what that stands for. If you were talking about sports analogies and we have the Timbers, they are a member of the MLS, Major League Soccer. So MLS means one thing, the organization called Major League Soccer. The Blazers, that would be the NBA is the acronym. But when we say KWH, we aren't talking about one thing. We're talking about 3 separate concepts laminated together into one acronym. So this chart is a handy chart to split that apart and not get confused by a group of professionals talking and throwing acronyms around. It's a very useful multi-part acronym. The first part is we go back to math and science classes in our high school and junior high experiences, and oh my gosh, the metric system. Yes, we are talking about K and M and G and T for tera. My favorite is the letter Y, which would be the iota watt, 10 to the 24th power. So the first part of the acronym is simply how many zeros are we going to put behind this measurement. So instead of 1,000,000 watts, we can say 1 MW, 1 megawatt. And those would be equivalents. On your bills, they're going to be kW. If you read the newspaper about power plants, you would be described in MWs. The middle part is the watt on your bill, kW. But it could be kV, it could be KA. So again, the middle part doesn't always have to be W. If you're talking about the power service to a large industrial plant, it might be 12 kV, 12.5 kV, 12,500 volts. So the middle part can be a lot of different terms. The third part is the one that is the most interesting that I find conversations with business customers, and that's the H, the number of hours a particular piece of equipment is being used. Quite often it's the one that has the least understood by customers. When I ask how many hours is this piece of equipment used in a month, well, it's about half the time, or maybe it's about a third of the time. They really don't track the hours, and yet that is probably one of the easiest places to find energy savings is looking at the hours and making sure something isn't on when no one's there, for example. Sometimes you will see an A there instead of an H, which stands for shorthand, the hours in a year. 365 days times 24 hours will give you 8,760 hours. So if you saw KWA, you know that somebody has divided that number by 8,760 to develop an annual average KW or MW. So this is the handy sheet when you start getting in conversations around the acronyms and G. You need to slow down and help understand it. So here's the basic formula we'll be using today for our examples so you get a good understanding of energy use and energy costs. Watts divided by 1,000 times the hours gets you the kWh, the W, the K, the H. And I like to separate those. Each one of those kind of depends on a certain amount of analysis or evaluation or questions you might ask staff of what's going on with the K or the H or the W. For example, if you had 20 light bulbs in a particular location at 100 watts each, then you have 2,000 watts, 20 times 100. If you wanted to know how much energy am I using per hour, you'd say divide by 1,000 times 1 hour. You'd have 2 kWh per hour is what that particular room full of light bulbs is using. Obviously, if I substitute other kinds of equipment or ask that question of an entire office building or campus, you might have 2,000 light bulbs or 250. So this is the first formula that you have to get a little comfortable with on energy use. So let's do a quick example. By federal code and law, every appliance, every piece of equipment has to have a label on it with at least the W, how many watts it uses. I'm showing you here the infamous incandescent light bulb of 60 watts. And through my interviewing, I discover it's on 10 hours a day, and it's on every day, Monday through Sunday. So that's a 30-day billing period, and I want to know, well, how many kilowatt hours a month does a single bulb use? So this is where you get a chance to participate a little bit and use your calculators. Oh, I've already given you the answer at the bottom. Well, there's the answer, 60 divided by 1,000 times 300, and you're all very bright and already know the answer is 18 kilowatt hours. But I have a plan. Let's swap that light bulb and change it to a compact fluorescent. Let's then say that for the same amount of light, it only takes an 18-watt compact fluorescent bulb. And now I want you to redo your calculation. How many kilowatt hours a month does this bulb use? Now, while you're doing your math here to come up with the answer, I have a little story about a business I encountered, an auto dealership. And a lot of the auto dealerships are lit up like crazy on their sales lots. And in talking to this one customer, they had 500 light bulbs. Well, if those 500 light bulbs were incandescents, the number was 30,000 watts, 10,800 kilowatt hours per month, and their monthly bill was $864 from all those very bright incandescent bulbs. And if they were to change those bulbs, they could save quite a bit of money, around $500 a month, by swapping them out. The tool, I don't see people using the arrow. My arrow would look like this. There we go. Denise is on there. There's my arrow. So if you click the upper left and you can move the arrow around. Edwin's got it. Twan's got it. Thank you. So we have a couple of different answers. Here's my math for calculating this one. If you take the 18 kilowatt hour bulb, the watt, divide by 1,000 times 10 hours at 30 days would be 300 hours. You should get 5.4 kilowatt hours a month per bulb. So this is a good way to practice your math and see this is why lighting is one of the first places you go to make sure that you get the best bang for the buck in your lighting. So here's a little quiz that I have fun with people. That this formula keeps showing up in all places in life, even if you're at the movies. So we're going to play Jeopardy a little bit, and the answer, the category is movies, movie titles. The answer is 1,210,000,000 watts is the answer. And I want you to use your cursors to raise your hand. And when you know what is the movie title I'm thinking of, I'm going to give you a hint, and let's see how many hands can go up with only one hint. The raise your hand is at the bottom of the participants window. There's my first hint. So please raise your hand when you think that you have. Shauna thinks she knows the name of this movie. A couple other people are chiming in. Fairlight knows. Twan knows. Looks like you're ready for a second hint. Here's my second hint of what this movie is I'm thinking about. If you look at the label, it would say 1.2 billion watts. And the final hint, of course, it's Doc Brown in Back to the Future, wondering where in the heck he's going to get 1.21 gigawatts. Is the label on that DeLorean time machine in order to get back to the future. And the science is actually pretty true in the sense that there was no power plant back in the history at that time that could give him 1.21 gigawatts. And I looked it up, and lightning is in this category. So the science behind Back to the Future, if you did have a flux capacitor, pretty true. So you can all turn your hands, lower your hands back down. That is, it shows up even then. Now the other question, by way of example here, that he might ask is, well, how many kilowatt hours does it take? What am I going to see on my electric bill? As every time I use this time machine, how much is it going to cost me in kilowatt hours? And here's the math. I'll move my cursor out of the way. The math is 1.2 million, or 121 gigawatts divided by 1,000. 1 second is the charge time, so that's 1/3600th of an hour. 333 kilowatt hours per trip is what this machine. If you were paying about 10 cents a kilowatt hour, that would be about $33.60 every time you took the trip. So the formula you have can be used in lots of fun places. Sometimes at work you're going to hear other terms that need to be converted. You might hear tons of air conditioning or tons of refrigeration. You might hear horsepower for motors, compressors, fans. Lots of moving parts. Drills are going to require motors. In the first case, there is something called energy efficiency. I need to pick up a circle here. There's an EER. That stands for Energy Efficiency Rating, or sometimes you'll see SEER, Seasonal Energy Efficiency Rating. These are pretty common terms, and in order to get to watts, you would have to take the tons and run it through this formula of times 12,000 divided by the rating gives you the number of watts. And what you can see here is the one that has the higher rating uses a lot less watts. If you run the math, even though both these air conditioners provide you the same amount of cooling, one uses 40% more energy than the other. This is really important not to have a purchasing standard or purchasing manager come to you and say, wow, I got a really good deal on a 5-ton air conditioner, but didn't pay attention to the efficiency rating because they just locked in 40% higher energy costs for the next 15 to 20 years by purchasing that piece of equipment. So check the purchasing standards for your equipment, and if there's an efficiency aspect to it that you need to get into the policy, it can be a very effective way to reduce your costs. If you look at horsepower, the same thing. The label will tell you whether it's 88%, 92%, or some other efficiency rating. In this case, if you bought the first unit, the 88% efficiency motor, you would have locked in 5% higher energy costs for every hour that motor is on. So let's talk about circuits, another aspect of using this formula where it can save you money. We talked about volts times amps equals watts. So I have here two motors, 60 horsepower motor on the left, a 60 horsepower motor on the right. They both are 48,000 watts, so they have the same efficiency rating. But in one case, it's a 480 volt is what you need at the plug. And the other case, it's a 240 volt unit. So I have a 480 volt machine using 100 amps to get my 48,000 watts. I have a 240 volt unit at 200 amps for the same 48,000 watts. So on the bill, they're both going to have the same amount of watts. But what does it mean to have 200 amp unit instead of a 100 amp? Well, bigger amps, back to our example of the garden hose, bigger hose size, I need bigger wire. If that's copper wire and it's bigger, that's cost you more money. If you have to go from one side of your plant 100 yards to the other side of your plant, that long run of copper wire can be a significant cost. And bigger wire has bigger line losses. So if you can, higher voltage systems will have smaller installation and lower line losses. So watch out for the amps. The other question that can come in is, oh, I'm out of capacity in my panel where all your circuit breakers are and you have to change the panel. I've had some very bright managers come to me and tell me, well, if they change their equipment, if it's at the end of life and can go to higher voltage, lower amps, in this case, they save 100 amps in the panel by swapping out a 240 volt unit to 480. So energy efficiency projects can have other benefits other than just the electric bill. So the other common question I get is, well, break it down. Give me a step-by-step process. So this would be my simple way of saying, find the W. That's the easy one. Find the label. Read the box, whatever. Get the watts. Add up all the watts in a particular room or system, and you'll have the total watts that are there. Then the K. That's an easy one. Divide by 1,000 because your bill is going to be in kW. Then the H, and this is the one that is often the most difficult, is how many actual hours of use does this system on during the month that you're trying to estimate. If you have those, then the only thing missing is the price. In our service territory, we're a little less than the average in the U.S. market. It's about 6 cents for industrial, 8 cents here in this example is commercial, and for residential about 10 cents. If you have those four things, you can then calculate the energy cost. The algebra way of approaching this instead of step-by-step is watts divided by 1,000 times hours times price. And some people are comfortable doing it in whatever sequence. So this is designed so that you could print it out, put it on a bulletin board wall, or just have it as a quick cheat sheet. So let's do some examples. Again, use your arrow tool in the upper left-hand corner to answer this. What I've given you is the cost of lighting a particular office area. It might be that you're leasing it out and need to make a calculation of what you should include for costs of lighting on the master meter or some other reason to understand the energy costs. Office area has 40 fixtures. Sometimes you'll hear lamps, and sometimes you'll hear fixtures. So ask for clarity. If each fixture has 90 watts, then you don't care how many lamps is in it. In this case, we'll deal with fixtures. Lights are on 10 hours a day, 7 days a week, so it's some kind of regular, scheduled business operations or school, and it's about 8 cents a kilowatt hour. Assume a 30-day in the billing cycle. So take your calculators and see which of these three do you think is the most likely monthly cost of running the lights in this particular building. Now, I have a story while you're doing those calculations of a person who went through a course similar to this. And what they did is they calculated the cost of each piece of equipment printed off a little label maker and put it on the equipment or near the switch in the room that pointed out, oh, this is what it's costing to use this piece of equipment, either per month or per hour. And they said they found that that made a difference. When you told people, here's the energy use of a piece of equipment, they were a little more judicious about when they used the equipment, how long it was on, those kinds of things. So you can have an impact by just making this information available to the people and the staff. Well, it looks like most people have collected around the 8640 number. I see you, David Christie's name. I think I've worked with David in the past. Glad to see you here. And here's my math. Interesting that it puts it behind all your names, but 40 times 90, I have 40 fixtures at 90 kilowatts, or 90 watts each. Divide by 1,000. The number of hours is 10 hours times 30 days is 300. Times the 8 cents gets you to 8640. So it looks like that this is pretty easy for this group. So let's move on to a second example. This is an example that shows you how to apply that to air conditioning, which is another common. HVAC is probably the single largest use beyond lighting in business applications. Customer has a choice between two units. One uses 1,200 watts, one uses 1,000 watts. They both drop the same amount of cooling, tons of air conditioning. Obviously, they have two different efficiencies here, and the one that is more efficient most likely costs you an extra amount of money. We make an estimate of 6 hours a day for 4 months a year, assuming a 30-day month. And the cost of electricity, to keep the math simple, I've said here is 10 cents. Just to keep it easy, you can almost do it in your head. The most common decision criteria for should I do this project, should I buy the extra efficiency is how long will it take to pay back the $100. This, of course, is called the payback period. The most common way to make decisions for capital projects that involve energy efficiency. So let's take a look at how we do this. Find the W is step one. In this case, I'm calculating savings. I want to know savings. So that's 1,200 watts minus the 1,000. There are 200 watts savings for every hour of use of this particular piece of equipment. If I divide by 1,000 to get to kW, then that leaves 0.2 kW. If I then figure out the number of hours is 720 hours, 4 months, 30 days, 6 hours a day, I've now got all the things I need to do the calculation. 0.2 kW times 720 hours times 10 cents. I save $14.40 a year. Doesn't sound like much, but given that you're only talking about justifying an extra $100, the $100 gets paid back in 6.9 years. Assuming this has a long life of 15 to 20 years, this looks like an economic possibility. Now, the longest payback period I've heard for most businesses is 5 years. Occasionally, I will hear 10 years payback in order to get tax credits or some governmental programs. So other businesses like restaurants might have a 2-year payback period. So each business unit, each company might have a different criteria. In this case, 6.9 is kind of long. I don't know if this project would get funded. There's one of our sponsors is the Energy Trust of Oregon, and one of the common ways they provide encouragement is to provide incentives, or occasionally they call it a rebate in some cases. So what it would happen here is suddenly they said, look, I want you to do this. We need the region to save energy. Let's throw a $50 rebate at this. If you get a $50 rebate, the math changes. Instead of $100, you have 100 minus $50 rebate divided by 1440. We just changed the payback period to 3.5 years. Now we're within striking range of that. What is the decision point? If yours is a 3-year payback, then you'd wait until the rebate is $60 or some other number. This is a great example to show that once you run the numbers on a project, you'd keep that list alive, keep that project sheet, check it every 6 months. It could be that the $100 goes down to 80, is the only difference between these two units. That might change the payback. The rebate might go up. The price of electricity might change. So those are all dynamics that change from time to time, and so you should keep a list and check the numbers and ask for a report from staff every 6 months. Hey, show me my projects and where we stand. Another good example, and this is one that I ran into when I simply went into a store and saw 2 light bulbs, both 25 watts, both produce the same amount of lumens. Lumens is the measure of light, not watts. And one was $4, one was $5, and the only difference was, again, read the labels on the boxes. One was an 8,000-hour life, and the other one had a 12,000-hour life. Now, you're in charge. You have to go out and buy 100 light bulbs for your building. Which CFL will you purchase? So again, use your arrow. There's not much math here I'm looking for, just a reaction. Which one of these bulbs, 100 of them, would you buy? The one for $4 or the one for $5? I see we have a pretty good group here. You're really interested in long-term savings, and most of you would pick the $5 bulb. A few of you might buy the $4 bulb. There's really no right or wrong answer to this one. What you will find is some companies who have very limited capital, they may be capital constrained and cannot afford the extra. So they may, in fact, go to the $4 bulb. If you have less capital constraints and can look at long-term savings, then the $5 bulb makes a lot of sense. For $1 extra, you're getting 4,000 extra hours of life. But there's a little more that you can squeeze out of this example. Here are the 2 bulbs again, and I've done some math. 10 hours a day at if they're on 10 hours a day every day during the year, you would be using this 3,650 hours a year. If you know it's going to last 8,000 hours and divide by that 3,650, the bulb that costs $4 is going to last 2.2 years before it has to be replaced. If you buy the $5 bulb at 12,000 hours, divide by 3,650, you end up getting 3.3 years. So you get over a year extra time on this purchase. I had a very bright manager come to me and say, this really helps in another way. In commercial applications, you have to recycle fluorescent lights, and most of the time that means you pay for that recycling service. Well, you just postponed it in a budget sense that you have less recycling costs in your budget by buying a longer life bulbs. So when you really think long term, over the next 6.6 years, you would have to buy the $4 bulb 3 times over 6 years. You would only have to buy the $5 bulb twice. 3 times 400 is 1,200. 2 times 500 is 1,000. You would save $200 over the period of years of consistently investing in the longer life bulbs. So those are a couple of perspectives that may help you change policy or change decisions on specific purchases. I think you're getting the theme here is the purchasing manager might be a really important person to clue in about these kinds of numbers.
Donna, and some of the comments are coming through also, less labor costs to replace the bulbs and maintenance.
Excellent point. If you're using staff to replace bulbs, if they're in hard-to-reach places, that labor hours can add up relatively quickly. So you've already caught on that starts with a simple energy calculation, but there are lots of non-energy benefits that you can get out of looking at more than just the watt. Look at the life, look at the efficiency, look at the other aspects of the equipment and systems that you're purchasing. Good catch. I'm going to steal that idea and add it to my notes. So what are the next couple charts? The next couple charts are, now that you're all excited about I can calculate numbers, and many of you are going to grab spreadsheets and run to a boss or a manager and go, look, look, look. A lot of management teams have a difficulty in looking at numbers and going, wait a minute, I'm overwhelmed by spreadsheets. Here I've taken monthly bills for a particular application and plotted 4 years worth of bills information onto a chart. If this is a spreadsheet, there'd be 12 columns for each month, and there would be 4 rows for each year on the chart. And you couldn't really see what's going on until you graphed it. And so when you look at the future and the complexity you're trying to explain things, shape means a lot and can be a good way to communicate to non-technical and non-numbers type folks. In this case, you can see that I put December in the middle of the chart because that is the highest bill, and I wanted the winter, which is where you get a lot of the heating load, to be in the middle of the chart rather than January through December. So the winter is in the middle. And what you've got here is 2 winters that were very high. I'm learning to draw with this thing. It's fun. And then you have the next 2 winters after we changed the equipment were a lot less, 40% less in the winter bills by replacing a heat pump system. Standard efficiency, when it got to its end of its life, it was replaced with a new high efficiency to do the heating in the winter. And that was on average about a 40% reduction in winter bills. Again, if you look at a spreadsheet, you might be able to see it, but graphically, it really highlights. And you can say, remember that project I talked you into, boss? Here's a graphical way of showing, here's was your bills now, before, here's your bills after. And that is a very convincing graphic to justify making the change. And quite often, this will be used to justify, gee, the next project you come to them and say, I want to spend money, this can build your credibility very quickly. What's coming in the future, and the future is now with PGE, we have digital meters on all the homes and offices and throughout our service territory that can give you hourly information. So I asked one of my experts in monitoring load software to give me a picture. This is a school. It is 30 days worth of metering information, and you've got a 24-hour clock at the bottom. So you go from midnight to midnight with noon in the middle. So noontime is in the middle, and sure enough, that makes perfect sense that at about 8 o'clock, everybody's at school, and you're at your peak loads. And then somewhere around 3 o'clock or so, people start leaving the building, and you have this slow decline back down to midnight. What you have is Monday through Friday up at the top. You have Sundays here, and you have Saturdays here. The 4 or 5 Saturdays, the 4 or 5 Sundays, and then all the Mondays and Fridays. So suddenly the chart can start making some sense once simple explanation. And you can ask some very smart questions without knowing any formulas or anything that's about energy. You can say, gee, something came on every single night and stayed on. Every single night. Comes on and it stays on. You have this definite shape over here. They finally, I heard, asked enough questions that the IT department said, oh, that's us. We have some software that turns on every computer in the school and backs up the data on it so that we have backups of all our data. But the software is not smart enough to turn the machines off. It only takes about an hour. What that means is if you bought the better software, you could drop this chart so that 30 days or 365 days a year, you could drop this chart and save all this energy in here. All this could go away and the shape would change. And you can do the calculation of hours at the bottom. You got KW at the left. You can calculate exactly how much savings that is and show it graphically. And you can also say if that stops happening, then the software is not working. So monitoring load in the form of shape and looking at blocks of energy like this can be a great way to use the formula, but the results are shown in a graph. The other interesting change here was not equipment, but was behavior. Why did it take so long to drop off from 3 to 4 to 5 o'clock all the way down to midnight? It turns out that it was a janitorial service. They would turn all the lights on in the school, and as they cleaned a room, they would turn the lights off when they left it. This let them know what rooms had been cleaned and what hadn't. Well, that's great for them, but the energy use is pretty dramatic out here. So they made a deal with the janitorial service to turn all the lights off and only have the lights on in the room that they were actually cleaning. They changed this shape to look a lot more like, get a different drawing tool here. Now the shape suddenly was way down here. It came down quickly, which means they saved all this energy in here. They saved it. And again, hours times kWh, you can calculate exactly. So by changing this shape, they can demonstrate, they can find and change and demonstrate energy savings. The last question they never got an answer on is why were Sundays running higher than Saturdays? I think they finally figured out that, we're renting out some space to a church group. There were some things going on. So sometimes you may be confused by a number, and the chart simply gets you at knowledge that you didn't have before about what's going on in a particular building. So you got formulas, you've got non-energy benefits and things to look for, like labor, like life, efficiency ratings. How do you get started? I would start with looking for changes in behavior. Conservation means don't waste energy. This is as simple as when you leave a room and turn the lights off. What are you changing? You're not changing the kW, you're changing the H. Maintenance of equipment. If you don't maintain your equipment, the efficiency starts getting worse and worse because you're not changing the filter, meaning more airflow. The system doesn't operate at its efficiency, and you've seen in one case 40% more energy use if the system is operating at low efficiency rather than its designed high efficiency. These are behavioral issues. Change the process. We mentioned the janitorial service changed their process for getting the job done, and that resulted in a reduced energy cost. Monitoring and feeding that monitoring back to people. Detect unexpected conditions. That's a process change. Change the equipment is the most common one that we started out with. When you purchase equipment at the end of its life, you have an opportunity to lock in energy savings for the next 2 to 3 to 20 years. So those are the three areas that I often encourage people to think about: changing behavior, changing process, changing equipment. So what are the next steps? I often get asked this question, and I always say the first thing is to get some kind of feedback process. Monitor what you're doing. Measure what's going on with pieces of equipment, and let people know about that. So when I say feedback, feed it back to the people who are using the energy. That's where I'd start. Compare that to other buildings or other industry standards. And we have many of those. We've got a staff here that can give you the standards for restaurants, for office buildings. Compare that monitoring use. Gee, if we're spending 30% on lighting and other buildings are only got 20% on lighting, why are we so much higher? And start asking the question and get some answers. Third thing is develop and maintain that list of project ideas. I know lots of cases where they came up with project ideas, and once they were rejected, they never went back. You've seen from this example that if rebates change, prices change, cost of equipment changes, it can change whether a project is yes or no. Every 6 months or so, redo the math on these things. The last one is keep learning to stay abreast. Technology changes, energy prices changes. We've got things like demand response and other tactics that you can use that are more sophisticated to reduce your energy bills. So once you've learned, that just is a starting point. Keep learning. Keep aware of what's going on. With that, if you do have follow-up questions, we've got two groups of engineers and lighting specialists available to answer emails or phone calls, and if appropriate, can even do a site visit. We've got Ann Snyder-Grassman has a team of people. There's her phone number and email. And John Maloney represents our industrial group. again, a phone number and an email. They would be more than happy to help you. And again, from the chart there, you can see, or the slide, you can see they work very closely with the Energy Trust of Oregon. They also know if there are tax credits available. They have lots of resources and connections to help you get answers. With that, I think I'm ready to turn it back to Lorena and see if we have any follow-up questions.
Thank you, John. And before we get started on the questions, I did want to remind everybody that we do have other webinars and seminars, and so visit our website to find out more. Join John again on July 26th to talk about the CFO's perspective of energy and energy efficiency and renewables, and he also talks about the ROI and all the terminology that the CFOs want to hear when calculating and sharing different projects in case you're competing with others on what you can do. There's also on HVAC and efficient lighting, so if you're looking for other technologies to calculate and improve savings and upgrades for your facility, please join us to those. And as a reminder, we will be emailing everybody the recording of the session and also the PDF of the material so that you can take notes and, like John suggested, pin that cheat sheet on your wall so you can be reminded on how to calculate energy costs. You'll notice under the participants window in chat, there's a polling that came up. Please take a few minutes to fill those out. We do like to get feedback from our participants to see how we can improve or what else we can offer. This is, we added this session as a result of requests from our customers, so we do pay attention and we do try to offer what you are looking for. So take a few minutes and fill that out. John, first question, but first of all, I wanted to point out your load shapes are a really good example of how to communicate to managers and supervisors how to save, not just how to save, but also what types of questions come up or what your facility is doing, and to prove energy savings. Because sometimes I know I'm a big visual person, and if you show me a chart, I'm not going to understand it, or I'm going to say, great, good job, but not necessarily understand where the savings come from. So I think that's a really good example of how you can use that. The first question, John, that came through is, what about the demand charges on the bill? Where does that come into play with the calculation and the formulas that you use?
That's a really good question. And the energy experts that I mentioned that are on our staff here remind me that on the energy bill, there is a demand charge for a lot of the commercial and almost all the industrial customers. Usually it's less than 10% of your energy bill if you separated your demand charges from your energy charges. And they advise that if you focus in on reducing the kWh, then the demand will go down with it. Now, demand is just kW. It's the highest number of watts that you're using during a half-hour period. Utility needs to know that because it has to build a system, transformers and wires, et cetera, that meet your peak demand. So it's a very helpful number for what is the load that we have to build to support. It also is a way to allocate some of those capital costs to the customers that have higher demand other than customers that have lower demand. So it's kW is the measure of demand. kWh is the measure of energy. Demand would be about 10% or less. If it's more than 10%, you definitely need to call somebody. It means you have some unique operations or something going on that is out of line on the typical business operations.
Thanks, John. You mentioned watts a lot in the formula, and you said look at the label. What label are you talking about, and what if there's no label on a piece of equipment?
The label I'm talking about most often in retail spaces, it may be on the box. So when you buy the box, if you turn it around on one of the sides of the box, you'll find watt ratings, lumens for lights. You'll see all kinds of specifications that are there by federal code. Often you'll find those same kinds of ratings in a kind of shorthand actually on the bulb or the fluorescent tube. In Motor's case, it's a metal nameplate. If you find a piece of equipment for which there is no label or it's been destroyed somehow or deteriorated, What you may end up meeting is someone who is familiar with equipment, an HVAC dealer, an engineer, a facilities person may walk in and go, oh, I recognize that. That's the Binford 5000. And once you have a name and a title, you can Google and find the specs online. In other cases, you may actually have to measure with a amp meter and a voltmeter what are the volts and what are the amps that this machine draws. And as you found out from the formula, volts times amps equals watts. So those are a couple of ways that you can get at a piece of equipment that doesn't have a label, or it's got a label that you can't read anymore.
What about for big commercial buildings like an office space where you have several, over 100 employees working? Where would you suggest that someone starts? And I know you gave some helpful tips and next steps. So where would you recommend that they start?
My assumption would be that the building has some kind of an energy management system that turns the lights off at a certain time and has some information that might be useful. So I'd immediately find who has control of that energy management system, where's the data, how can I get at it, and start building the benchmark. The second thing is you need to develop some kind of a feedback mechanism to the people in the building, because a lot of the energy use is going to be driven by the people in the building and what they're doing. So one of the things you can do is we have a course called Energy Champions Seminar. There are others out there you can connect with that are championing energy efficiency and energy use and sustainability, and make a connection with the network. And, of course, again, you can call us, and we can help you get started as well, Ann Schneider or John Maloney.
John, I know you're not an expert in lighting, but people that have heard that the T12 bulbs are going to be discontinued, and if so, when is the deadline to change out? Do you know anything about that?
I don't know much about that other than the codes are changing, and this is a very hot topic. We have on staff a Mark Whitney, who is a lighting specialist as well as Green Building certified, works for Ann Schneider. So if you have specific questions like that, I would definitely email Ann that question, and she can forward it on and get you some answers. We also have some seminars on that. We just had a big lighting conference. So keep an eye out for seminars or future webinars that are focused in on lighting. We have Intro to Efficient Lighting and Controls on August 30th. That would be a great question. And Lorena, that is Mark, I think, isn't it? So Mark Whitney will be the instructor for the August 30th upcoming webinar. That would be a good one. But if you need an answer now, you can certainly email to Ann and get through to Mark. It is a dramatic change when codes change, and that's another reason why you want to keep your projects alive and keep looking at them and going, what's changing in technology?
Yeah, thank you, John. I believe Mark will be covering that topic. If not, we'll make sure that we ask that question during the Efficient Lighting and Controls webinar on August 30th. So hopefully you can join us for that one. That was the last question that I got, John. So we will stay online a little bit longer if you still want to submit some more questions or want to submit any thoughts or recommendations. Again, take a few minutes to fill out the polling, and we'll follow up with all the details within a couple days. Thanks again for joining us.